Hey there, Calc 3 folks, back here with another quick video in our study of vector calculus, where we're looking at this concept of a surface integral, where in our last video we looked at the surface integral of a function. We are going to now consider the calculation for a surface integral of a vector field, and specifically look at what we call surface flux, or the flux across some surface, right, caused by a vector field, right? And what we note here, along with being able to apply the surface integral operator to some scalar value function little f, the surface integral operator, right, the process of integrating over some surface can be applied over a parametric surface S in three-dimensional space in some vector field f bar, right? In some vector field f, resulting in the interpretation of the flux of the field, the vector field, across S, which is defined as follows. All right, and what we do obtain here is a rather similar looking calculation, right? Notation wise and in terms of calculation here for surface integrals. By definition, we consider having this surface S that's defined parametrically in R3 by some multivariable vector valued function with parameters u and v, where u and v are in some region of space R defined in 2 dimensions, right? If this surface S occurs in a vector field f bar, the flux of f bar across S is given by this calculation here. And we understand that this calculation is coming from what we have here is what we might call the normal behavior to the surface S. We are integrating the field in the direction of the normal behavior to our surface S, which is going to come from this double integral calculation, this double integral that involves as an integrand, right, this dot product, this double integral over region R, which defines our parameter space u and v with respect to the area of R, where what we integrate is the dot product of our vector field written in terms of those parameters u and v with the what we would say is this cross product calculation, the vector given by the cross product of t bar sub u with t bar sub v, where how do we again understand t bar sub u and t bar sub v is they are these partials of the parametric description for surface S. It's the partial with respect to u for r bar of u comma v for t bar of u, and the partial with respect to v for r bar of u comma v, right, in this vector, well, yes, in this vector field over this surface S that's been defined parametrically by r bar. All right. Let's see. Now this is one thing we do note is that the direction of this flux measurement with respect to the orientation of the surface is consistent with applying the right-hand rule to these two vector descriptions. If we apply the right-hand rule, placing our hand on this vector, our right hand on this vector, and curling the fingers on the right hand towards this vector, right, the flux will be in the direction that our thumb will be pointing on that surface. All right, that is using the right-hand rule for orientation. Now we might consider an example here where we consider calculating the flux of the vector field described by this radial vector field xyz over the surface S, which has been defined parametrically as this planar surface seen here. The planar surface defined by r bar of u comma v, where the x component is u, the y component is v, and the z component is described by the plane 10 minus 2u minus 5v in terms of u and v, those parameters u and v. Where when we think about u and v in this case might exist over region R, where region R, or exist in region R, where region R is this two-dimensional space defined by the coordinates of u and v, where in this case we might consider u to be between the values of 0 and 5, and v to be between the values of 0 and 2 minus 2/5 of u. Right? And what we are describing is what we might see here in this illustration. We have this surface S occurring in this vector field, highlighted by all these arrows, where this vector field is occurring across S, right? Where we're interested in the outward flux of this field across S, or the flux across S for this vector field, where the surface S, where the surface S has been defined parametrically, right, as existing over this region of R, right, where R is defined by values of u and v, which correspond to x and y in our description of space seen here, where if x is u and y is v, then z is just 10 minus 2u minus 5v, or the surface seen here in space. Right? R being this triangular region described by these bounds on u and v. Right? So what is the flux of this field across this surface S as we've defined it? Well, we do take note that in that parametric description, the vectors t bar of u and t bar of v are given by the vectors 1, 0, negative 2, and 5, or 0, 1, comma, negative 5 in that space, right? At any point in that space. Well, I should say over that surface in that space. These are the descriptions of these partials of our across our surface, right? Where the cross product then of those vectors right, is given by this calculation here, where we again just calculate the determinant of this 3x3 matrix involving those that row of standard unit vectors and then the two rows of the corresponding vectors in our cross product, where if we follow that cross product operation for that determinant, we do obtain the vector 2, 5, 1. Now this vector 2, 5, 1 is going to be dotted with f, written in terms of u and v. And if we consider that value inside of our double integral, right, well, you might note for our field described by x, y, z equal to what we might call x, y, and z, right? Since, let's break this out here, right? Since r bar u is defined by this surface here, f bar in terms of u would be described by this vector field seen here, u, v, 10 minus u, 10 minus 2u minus 5v. This is describing the vector field on this surface. This is describing this behavior x, y, z on this surface with respect to u and v, these parameters u and v. And then the flux of f bar across that surface S will be given by this double integral, the surface integral, across the vector field orthogonal to the vector field, right? Which is equivalent to this double integral calculation seen here, where we are going to integrate over that region of R, where R, we had noted, is this region here defined in terms of u and v, u between 0 and 5, v between the functions of u, 0 and 2 minus 2/5 u, right, describing this region of space seen here, right? With respect to the area of that region, with an integrand given by the dot product of this vector, u, v, 10 minus 2, u minus 5v, with 2, 5, 1. where if you take a moment to calculate the dot product, you will see you get 2u plus 5v minus, plus 10 minus 2u minus 5v, where you will notice the 2u and the 5v do cancel with each other, right, within that integrand. If we consider the dot product here of those results, we do get 2u plus 5v plus 10 minus 2u minus 5v, where the 2u's and the 5v's cancel in this calculation, leaving you only with the value of n. And you are going to form the double integral over this region R defined between values of u from 0 to 5, v from 0 to 2 minus 2/5 u, where if you integrate just 10 with respect to v, that is 10v, where 10 is a constant multiple, we might bring that out in front. V evaluated across these bounds would just be 2 minus 2/5 u, where 2 minus 2/5 u now can be integrated with respect to u, which is 2u minus 1/5 u squared, where evaluated from 0 to 5 is 10 minus 5 in value, or 5 inside the bracket. So the 10 as a constant multiple outside times the 5 inside the brackets leaves us with this measurement for the flux of the field across the surface S, defined parametrically, given by this measurement of 50 units, right, for that flux. All right, folks, what we have calculated here is our flux calculation across a surface, right? The flux of this field, the amount of the field that is moving orthogonal to this surface, as we've defined it in the parametric description above here, is given by the value of 50 in this double integral calculation, where this double integral is going to involve integrating, right, that surface integral in the context of, well, I should say over the region R in two-dimensional space, where to translate the surface S into R, you do have the scaling factor incorporate itself into the integrand, where the scaling factor times dA is what's replacing the n times the ds, the rate of change in the surface area. All right. Now, again, folks, this is a surface integrals of vector fields, where we use a surface integral of a vector field to calculate what we call the surface flux calculation. All right. Now, what we will see ourselves come back to is actually also being able to use the surface integral of a vector field to calculate the circulation along the boundary of a surface. And that is the topic we approach in the next section of notes, looking at Stokes' theorem. Stokes' theorem looks at using surface integrals over a vector field, right? The surface integral of a vector field to calculate what we would think of as being circulation along the edges of some surface. That is going to be our second to last section here, folks, and I'll have a video out for you on that shortly, but that does conclude looking at this calculation for surface flux. All right, so I hope you're hanging in there. I hope you're doing all right. We are, like I said, almost done here, folks, and we will be back in just a couple more videos to wrap it all up. So I'll see you then.